All right, so we're now going to do the post-lab calculations for the antacid back titration lab. So this is your post-lab calculation sheet, and I actually have my data on another sheet so that I can copy it over a bit more easily. So the first things we're going to need to copy over are our burette findings. So we've got Alka-Seltzer. My Alka-Seltzer, I started with 14.2, if that would right, 14.2 milliliters. I ended at 21.2 milliliters, which is a difference, that's what we're finding right there, a difference of 7 milliliters. So that is how much of the 1 molar sodium hydroxide we used, was 7 milliliters. Okay, for Tums, we started at 21.2, and we ended at 26.7 milliliters. So these are my numbers from the videos. If you haven't watched the videos of the lab, these are where I'm getting these readings from. And that is a difference, if we subtract those numbers, of 5.5 milliliters. All right, so we want to use this information now to find out how much of our hydrochloric acid was neutralized by that sodium hydroxide. And we can do this because this is a titration reaction. So in a titration reaction, we have an acid and a base that are coming together. So we'll go ahead and remind ourselves that. I'm writing this down. So in a titration, add a bit there. In a titration, we've got our acid that is going to react with our base, and together they will neutralize, meaning that the acid will no longer be acidic, base will no longer be basic, and instead will produce water, which is neutral. We'll produce some sort of salt, also neutral. And in the case of our reaction, we also produced carbon dioxide. Okay? So that is our titration reaction. And at our equivalence point of the titration, so that is right around when it changed colors, that's what we were trying to find. At our equivalence point, the amount of the acid in moles will equal the amount of the base in moles. So our acid is going to equal our base. The other way we could write that is that our hydrogen ions or our hydronium ions will equal our hydroxide ions. In this case, specifically, we used hydrochloric acid, so our hydrochloric acid is going to equal out with our sodium hydroxide, again in moles. Okay, so using that information, all we need to really find is the moles of sodium hydroxide used, and therefore we know that that's the moles of hydrochloric acid. All right, so we had 1 molar sodium hydroxide. And I have my data right here as far as how much I used, so that's going to be my volume. So we're going to use our molarity equation to find moles. So my molarity equation is M equals N over V, where M is my molarity, or my concentration, N is my moles, and V is my volume in liters. All right. So we're going to plug all of that information in now. And so we'll have that our molarity, we used a 1 molar sodium hydroxide solution. So 1 molar. We're trying to solve for moles. And our volume here. So I had 7 milliliters. Well, that's in milliliters, and I'm going to need to convert it actually to liters first. So to do that, I'm going to move my decimal point 3 times. So I'll add 2 zeros, and that will be 0.007 liters. 0.007 liters. Okay, and now I will cross multiply to solve. So that will mean N equals, well, anything times 1 is itself. So N equals 0.007, and N is moles, so that's what we're solving for, is moles. And that was moles of sodium hydroxide. But recall that our moles of sodium hydroxide is equal to our moles of hydrochloric acid at that equivalence point. So therefore, we're trying to find out the amount neutralized, which would be the same amount here, 0.007 moles of hydrochloric acid. Okay. So I'm going to go ahead and add that to my paper, 0.007. And so you might already have noticed the pattern, but I had 7 milliliters here. I moved the decimal point 3 times and changed it to moles. So based on that logic, this would be 0.0055 moles. And it is, in fact. We can do the math as well to show that. But that would also be a 1 molar solution, solving for n. And my volume would be 0.055. Once we cross multiply, we would see that n equals 0.055. And that's moles of sodium hydroxide, which is also moles of hydrochloric acid. All right. So our next value says that we want to find the initial amount of hydrochloric acid, because when we did our titration, some of our hydrochloric acid had already been neutralized by our antacid. So we are now needing to find the moles, the initial moles that we started with. So our initial moles, we can calculate that also with the molarity formula. I gave you all 25 milliliters of hydrochloric acid, and that was a 0.5 molar solution. So we'll use the molarity equation again, M equals N over V, but this time we'll plug in our initial values for the hydrochloric. So 0.5 molar equals N over our volume. We have to convert our volume into liters, so we'll move that decimal point 3 times. So that becomes 0.025 liters. I'm going to cross multiply, and here 0.5 times 0.025 gives me 0.0125 moles. So that's how much I started with in that acid before we added it to the antacid and before we titrated it. It's 0.0125. So I'm going to add that here. And that would be for both the Alka-Seltzer and for the Tums. So everyone's answer should be the same for this box. So that is what we started with. Your answer above, this is different. This is going to be based on your experimental value, so based on your volumes. The next step is we want to find out how much of the hydrochloric acid was neutralized by the antacid. So we know how much was neutralized by the sodium hydroxide, and we know how much we started off with. And so those two should add up together. So we had our hydrochloric acid, and it was going to be neutralized by, first our antacid, and then it's going to be neutralized. All right, this is neutralized by our antacid and then our sodium hydroxide. So if we know that we started off with 0.0125 moles, and then over here I had, for at least my Alka-Seltzer, 0.007, I need to find out how much was neutralized by my antacid. So I can do 0.0125 minus 0.007. When I do that, I get 0.0055. So that is the amount of moles of hydrochloric acid that was neutralized by my Alka-Seltzer. All right, so I'm going to add that in here, 0.0055. So notice to do that, I subtracted this smaller number from my larger value. The same thing here, 0.0125 minus 0.055. And that gives me 0.007. It's interesting how my numbers are actually kind of opposites of each other. It was weird how that worked out. That is how it ended up happening. Okay, so we can kind of quick review. What we've done so far is use the molarity equation and a lot of subtraction. So we subtracted these values to find out how much we used of sodium hydroxide by volume. We converted that from milliliters to liters, and then used the molarity equation to convert that to moles. From there, we also found the initial amount of hydrochloric acid in moles, and then we subtracted these two values to get these. So 0.0125 minus 0.007 gives me 0.0055. 0.0125 minus 0.0055 equals 0.007. It's weird that my numbers worked out this way, that they were kind of opposites. Yours probably aren't this, I don't know, magical in how that worked out. Okay, so from here, it tests for the same thing, but notice it is now in grams. So we're trying to find the amount of hydrochloric acid neutralized by the antacid in grams. So we're going to take these numbers and we're just going to convert them into grams. Okay, I'm running out of paper. Let me grab more paper over here. So I've got that I had 0.0055 moles of hydrochloric acid. And then that I need to convert into grams. So I will need to use molar mass. So 1 mole of hydrochloric acid is how many grams? Well, to find this, I'm going to pull out my periodic table. So I've got my periodic table here, and I'm going to add up the molar masses of each of the individual atoms. So I've got hydrogen is 1.00794, and chlorine, and I'm reading the decimal number on the periodic table, 35.4527. When I add those up, I'm actually going to round to the first 2 decimal points, and I get a number of 36.446. And that is in grams per mole. Oh, realizing you can't see all that. 36.46 grams per mole. Okay, so we're going to take that number and put it right here, 36.46. And now we can use our conventional analysis to convert this into grams. So 0.0055 moles of hydrochloric. The moles of hydrochloric will cancel with this moles of hydrochloric. And then we will be left with grams of hydrochloric. So I'm going to get out my calculator. I've got a calculator here. 2.055. Oop. Skipped a 0. Make sure you have the right number of zeros. 0.0055 times 36.46 gives me a number of 0.20053. And now that is in grams of hydrochloric. Okay, I'm going to go ahead and do my other problem as well. So 0.007 moles of hydrochloric. Convert that using the same conversion factor, where 1 mole of hydrochloric is 36.46 grams of hydrochloric acid. And then I will multiply across 0.007. Do this so you can see it easier. 0.007 times 36.46. We don't have to do any division because we just have a 1 on the bottom. And that gives me a number of 0.25522. And that's in grams of hydrochloric as well. So let's go ahead and copy those numbers onto my chart. And 0.25522 grams. All right, so based upon this, I can see that Tums neutralized a little bit more than my Alka-Seltzer, but it was still kind of roughly the same. But we want to find what's called the antacid neutralizing capability. That's abbreviated the ANC. Again, standing for antacid neutralizing capability. Okay. And so that is going to be this last box here, our effectiveness by weight. So we know how much the Tums and Alka-Seltzer reduced or neutralized our acid for grams of acid, but we also want to know based upon per gram of antacid. So we're going to take this number now and we're going to divide it by the weight, the mass of our tablets. Okay, so what I mean by that, let me show that on paper as well. So I've got this number here, of 0.20053 grams of hydrochloric acid. I'm going to divide that by my Alka-Seltzer mass, which is 3.05. And then, let's see, 0.2053 divided by 3.05 gives me 0.0657. And that's grams of hydrochloric per gram of Alka-Seltzer. Write that down here, 0.0657 grams of hydrochloric per gram of Alka-Seltzer. We'll do the same thing for our Tums. So we've got a value of 0.25522 grams of hydrochloric. We'll divide that by the mass of my Tums, which was significantly less, 1.93 grams. So I've got 1.93 grams of Tums. Punch that into the calculator. Equals 0.132 grams of hydrochloric per gram of Tums. So now we can better compare these numbers, because previously when we were comparing them, it wasn't really an even shot. Now we're comparing it per gram of our antacid. So now we can see that our Tums seems to be significantly more effective than our Alka-Seltzer when we compare it per gram of our antacid. So a few more questions for you to answer, but I wanted to turn your attention actually to the back because I made a small mistake here. And I wrote calcium carbonate both in the reactants and the products. So this is not calcium carbonate here. This should be calcium chloride, CaCl2. And why that's important, and we're going to take a closer look at these reactions actually right now, is we're going to look and see if they're balanced. That was part of the pre-lab. I wanted you to look at them. So we'll look at the reactions for Tums versus Alka-Seltzer. And in our Tums reaction, we have calcium carbonate. It's our active ingredient. Reacts with the hydrochloric acid in your stomach to produce water, calcium chloride, which is a type of neutral salt, and also carbon dioxide. Alka-Seltzer is a similar reaction. It is sodium bicarbonate, NaHCO3, reacting with hydrochloric acid to produce water as well, plus salt, that's actually table salt, and carbon dioxide. So we'll look to see if these are balanced. We'll start with Alka-Seltzer. We've got a sodium on, looking each side of that arrow, one sodium on each side. We've got 2 hydrogens on the left, and I see we've got 2 on the right, so that balances out. Got 1 carbon on the left, 1 carbon on the right, 3 oxygens on the left, and 1, 2, 3 on the right. We already did our hydrogens, so then chlorines, we've just got 1 and 1. So that is a balanced equation. And for here, let's look at our Tums. Tums, we've got a calcium and a calcium. Looking again on the left and right side of the arrow. We've got a carbon and a carbon. We've got 3 oxygens, and we've got 1, 2, 3 carbons. For our hydrogens, I've just got 1 on the left, but I've got 2 here. So what we're going to do is go ahead and add a number 2 right in front of the hydrochloric. And that should also help with our chlorines because now we have 2 chlorines on the left and 2 chlorines on the right. So we did have to add a coefficient, but now this is balanced. And this is very important to our reaction because we want to look closely at the mole ratio between our active ingredient, calcium carbonate, and our acid. So the mole ratio here, we don't have a coefficient in front of calcium carbonate. So that can be assumed to be a 1. So that means our mole ratio is a 1 to 2. 1 to 2 ratio. For our Alka-Seltzer, our active ingredient is sodium bicarbonate. And we want to compare that to hydrochloric. So for our mole ratio here, it's going to be a 1 to 1 ratio because we don't have any coefficients in front, so we can assume a 1. So just based on the reaction and looking at this, we can see that our Tums should be more effective because our Tums, for every 1 mole of our calcium carbonate, our active ingredient, we're neutralizing 2 moles of our acid. It's a 1-to-2 ratio. With our Alka-Seltzer, it's a 1-to-1 ratio, so every 1 mole of sodium bicarbonate neutralizes 1 mole of acid. So based on this, our hydrochloric acid should be half as effective as our Tums. Or another way of saying that is that our Tums should be twice as effective as our Alka-Seltzer. I think I just said hydrochloric a second ago. So our Tums should be twice as effective as our Alka-Seltzer. So let's look back at our numbers and see if that lines up. So I had that my effectiveness for my Alka-Seltzer was 0.0657. Let's see if I multiply that by 2. I get 0.1314, which is very close to what I got for my Tums. So my Tums and my Alka-Seltzer are, pretty much different by a factor of 2. That my Tums is almost 2 times greater than actually it's slightly over 2 times, greater than my Alka-Seltzer's effectiveness. So we could have simply looked at the balanced chemical equation to determine this efficacy, but it's probably more fun to do the lab. And it's cool that our lab results match up with our balanced chemical equation. All right, I'm going to have you do the rest of these. For moles of Tums and Alka-Seltzer, make sure that you're looking on the Google Slides presentation and using your conversion factors to change it first from milligrams to grams, and then from molar mass, use molar mass to convert from grams to moles. All right, thanks for watching.